So another type of optimization problem is one like this, which is kind of the open box type question. Okay, so in this case, we've got a problem that's just in 2 dimensions because we're just looking at area. So we've got a rectangular plot of farmland enclosed by 180 metres of fencing material on 3 sides. The 4th side of the plot is bordered by a stone wall. Find the dimensions of the plot that enclose the maximum area. Find the maximum area. Okay, so it's a geometric problem, so it's useful to draw a sketch. Okay, so we've got a rectangular plot. So here's my rectangle. It's enclosed by 180 metres of fencing on 3 sides, and the 4th side is bordered by a stone wall. So here we've got our 4th side, okay? And the fencing goes on just these 3 sides. Now, if we let the shorter sides be x and the longer side be y, for example, we know the area is x, y. We also know that if the total length of this fencing is 180, then 180 is 2x plus y. So y is 180 minus 2x. And this is a fairly standard sort of setup to a problem like this. So it is worth learning how to do this. Okay, you probably would have come across it in IGCSE as well. So we know that the area can actually be written as x times, and then we substitute in this expression for y. So it's x times 180 minus 2x. Okay, and if we want to be really fancy, we can say that the area in terms of x, a of x, is this. And I'm just going to expand it out for the purposes of differentiating it later on. So 180x minus 2x squared. Okay, so this is now our important formula that we're going to use to find the dimensions of the plot that enclose the maximum area. So it's a maximum. So we're looking for a local maximum. So we want to differentiate it. Okay. So if we differentiate it, we've got 180 minus 4x. And we want to know when the gradient is equal to 0. Yeah, so in other words, when's our local maximum or minimum? So 180 minus 4x is equal to 0. So 180 equals 4x, and that gives us that x is 180 divided by 4, 45. Okay, now that's the maximum area is when x is 45, but we need the dimensions. So we also need the y value. So remember, y is 180 minus 2 times 45. So y is 90. Okay, so the dimensions for the maximum area are 45 and 90. I assume it's in meters, yeah, meters. Okay. Now that's an answer. If that was a question in the exam, if that's all the question was, that's your answer, and that's absolutely fine. We also need to find the maximum area. So the area is 45 times 90. And I'll just quickly use a calculator to work that out. Sorry, I should have had that already for us. 45 times 90, 4,050. Okay, square meters. Now, if that's all the question was, that's fine. You're done. But more likely than not, it's also going to ask you to prove that that is the maximum area. Yeah. So to prove it, we can think about 2 things.
If we look at this here, it's a negative quadratic. Okay, so you know it's going to have this shape. Sorry, it's a negative quadratic, so it's going to have this shape. Yeah, so clearly that's a maximum point. But if you absolutely had to prove it, then you're just going to have to find the second derivative. So the second derivative is -4, and therefore the second derivative is always negative. Yeah, it's concave down because the second derivative is negative. In other words, the gradient is always decreasing as we move from left to right. Okay, so basically that tells you straight away, therefore, that this is a maximum point.